Fractals are an exquisite mix of art and mathematics. Although they're only about 30 years old, they've caught the imagination of mathematicians, artists, and even the general public. We will explore the definition, history, construction, and applications of fractions. Let's begin with a small introduction. A fractal is a set of points whose fractal dimension exceeds its topological dimension. This is a fancy way of saying it's not 2D and it's not 3D, it's somewhere in between. It has a fractional dimension. A fractal includes a seed pattern that is then scaled down or up and rotated and then repeated over and over. We say that this fractal is self-similar because it's just a bunch of the same image over and over again. When we zoom into the large image and just look at a piece of it, it looks just like the large original. You can design a simple fractal by just choosing a simple geometric pattern and then applying a rule over and over. Repeating the rule is called a recursion. Each time the rule is applied is called an iteration. For example, look at this large plus sign on the left. This is our seed image. The rule is to shrink the plus sign to half and then glue it onto the ends of the original plus sign. See in the middle, the first iteration, where there are plus signs hanging off the end of the original plus sign. The next iteration happens when we use recursion to do it again. Shrink the original one again half, so it's only quarter size, and glue it onto the ends. We could keep doing this infinitely long. However, I only show 3 iterations here because it gets hard to draw. Gaston Julia was a French mathematician who published a book on the iteration of rational functions in 1918. Since this was way before computers, he had to draw the sets of functions by hand, and these types of fractals are now called Julia sets. You can see an example of a curly Julia set at the top of the page here. Benoit Mandelbrot was a mathematician who worked at Yale University and only died last year. He was able to use a computer to explore Julia's iterated functions and then found a universal equation that included all of the possible sets. This Mandelbrot set is named after him and is becoming famous as an icon. There are an infinite number of Julia sets, one for each complex number in the complex plane. Every time you choose a complex number to be the constant or the seed, then you iterate over and over, it generates a picture like the Julia set. The computer chooses the color for what happens with the iteration. For example, if we get out your calculator and you put square root and program it into your calculator, we can start with the seed number, say 256. If you take the square root of that, you get 16. If you iterate or take the square root of 16 again, you get 4. If you take the square root of 4, you get 2. If you take the square root of 2, you get 1.41 something. If you keep iterating the original number 256 with the rule of take the square root, where are the numbers going? If you had a t-table, where would those numbers be heading? It looks like they're heading to 0. Will they ever reach 0? Will they ever go negative? The computer would choose the coloring for this particular constant, 256, in this very simple example, to be a color that represents eventually goes to 0. In the Mandelbrot set, these are colored black and makes the funny little bug shape in the middle. Now, you might choose another function that might go to infinity when you choose a seed number. Those might be colored purple in our picture. And maybe if they flop back and forth between 2 values, or jump all over the place, or settle into a cycle, then we could color them yellow or orange or red. Those are the points that are close to the black in the image. There's a lot to explore with the Mandelbrot set. There are lots of different equations, and you could look at the relationship of the Julia sets to the Mandelbrot set or the universal set. Fractals come in many different types. Here's an example of some that you might see. Fractals that look like clusters, fractals that look kind of like Julias. There are mini-brots. Some go in spirals. Some go in what this website calls a nova. More fun is to zoom into the Mandelbrot set. We can look at it and explore it. This website is the best one I've found for exploring the Mandelbrot set. This particular Mandelbrot is rendered in blue and white, with black, of course, for those numbers that take you to 0. But we can draw a rectangle around any part on the picture and click Go, and it zooms in. Can you see that the wart on the original Mandelbrot has its own warts? If we want to zoom into a wart, we see that that wart has warts upon it. And this goes on almost infinitely. Let's pick a little wart and see what happens. Little warts have little warts on them. And what's this funny little black thing here? A mini-brot. There's 2 of them here. All kinds of things are hidden here. If you get tired of looking at the black part, just put your rectangle around some of the colorful part. This almost looks like river deltas. There's a mini-brot hiding right there. We can keep zooming in, checking out, looking for exciting things. You can look at the lacy parts. You can look at the intersections. This software actually will go in 30 or 40 times before you max out the microscope idea here. Now, sometimes when we go, we might find another mini-brot somewhere. We can go hunting for mini-brots. You can go to this website. It is mathforum.org, or just search for Alejandres and Mandelbrot. Here are some other examples of simple fractals. Can you identify what the original image may have been and what the rule is that's being done over and over? For instance, in the Star of David, can you tell that the original one was a 6-pointed star, or a Star of David, and then each section on those were replaced by smaller stars of David, which were then replaced by smaller stars of David? Each of these have about 3 iterations before it gets too complex to render in such a small picture. You might look at some interesting ones, such as the Koch curve. This is often called the snowflake curve and is fairly popular in mathematics. It was started by a mathematician named Koch. It's something that you could do with your students, especially if you have any kind of interactive media. Another interesting one is a Pythagoras tree. Notice this one's very symmetric. They always start with a square on the bottom, but you choose what type of triangle to put on top of the square, and then notice it iterates. Square, triangle, square, triangle, square, triangle, square, triangle, all the way around till it makes what looks like leaves. This particular triangle happens to be a 45, 45, 90 isosceles triangle. If you chose a different triangle, your tree would not be symmetric and would look very interesting. Google it and see what you can find out about it. Here's an example of an iterated function system. These are objects that are often used to do pictures of items and not just simple sketches. For instance, this fern could be referred to as an iterated function system and was actually generated on the computer and not just taken a picture of out in nature. The artist started with a little teeny tiny piece like this, which he then shrunk and glued along a stem until he made this frond. Then that frond was shrunk and glued along a stem until it made this entire fern. If we were to zoom into this fern, we would see that the entire shape can be found in the smaller shape, which can be found in the smaller shape, which can be found in the smaller shape, and etc. This is an excellent example of self-similarity. Wacław Sierpiński was a Polish mathematician who's famous for his Sierpiński's triangle. Here we see a 6-iteration example of how to make the triangle. This is another activity that can be done in the classroom. In fact, if you use triangular dot paper and use 27 dots on each side of this equilateral triangle, students can construct it with a ruler. We start with an equilateral triangle. Then we measure the midpoints of each side and connect them. This center piece is left alone, or in some instances we color it in. And the outside 3 triangles are then again measured to find midpoints and connected. Again, the centers are removed, colored, or ignored. We keep doing this with the outside triangles, noticing by the 6th iteration it's getting pretty lacy looking. This is a famous fractal. However, it's not the only Sierpinski type fractal. The Sierpinski carpet is started with a square, which is then divided into 9 equal sections. The center section is punched out, colored in, left alone, however you want to deal with it. The 8 outer squares are then divided into 9 subsections, and again, the center is left alone. The others are divided into 9 sections again, over and over until it makes this lacy carpet. The Sierpinski pyramid and the Sierpinski cube are 3-dimensional representations that are formed the same way, by punching out or removing a specific shape over and over as they iterate. Now, fractals aren't just pretty pictures. If you were to look in the back of your cell phone, you might just see something familiar. Do you see this fractal antenna? It looks like a Sierpinski carpet. It's a way to save weight and money on a copper antenna. There are many other ways that we can use fractals. We've had several medical advances in AIDS, cancer, bone fractures, and heartbeats that are all fractal in nature. And here's an example of an animal lung. Now, if you're an animal lover, you may or may not like this idea. These are actual representations of the inside of an animal lung. Dogs, pigs, manatees, etc. Look how fractal they are. Scientists work with fractal geometry to locate oil, identify geologic faults, and even predict earthquakes. They can model acid rain and corrosion spread using fractal geometry. Even trying to understand where our universe came from, or the Big Bang Theory, can be improved by using fractals. In industry, fractals are used to test spring wire, to test stress loads on oil rigs, and to look at turbulence effects on aircrafts. You can also use it for image compression algorithms to store images and pictures and to retain definition or details of those pictures. The weather and the money market are also very fractal in nature and can be modeled that way. The military uses a fractal footprint, which then can be used to identify man-made versus natural features on aerial mappings. As they take pictures of rainforest, they can use this fractal modeling to identify straight lines that would be man-made versus fractal patterns that would be in nature. They also track submarines this way. Mother Nature has many fractals. Here are some examples. Lightning, river deltas, veins in leaves, and look at this weird vegetable. This is actually a cross between broccoli and cauliflower. You can sometimes find it in the specialty stores. River deltas, seashells, snowflakes. There's a bigger picture of the Romanesque broccoli. We've seen the ferns. Look at this plant from underneath, the Queen Anne's lace blossoms from underneath. Broccoli, normal, peacocks. All of these can be talked about as having a fractal nature, a pattern that is repeated over and over and over again. Fractals are also used in movies and video games. In fact, many of your movies that you see nowadays are not filmed on location. They're just made on the computer. When we first were introduced to Tatooine, the Star Wars desert, it was done on site in the Sahara Desert. However, all the follow-up movies, all of the landscapes were generated on a computer, including all of the Tatooines. Here's a website that shows several ideas for landscapes, and I'm going to show you part of this video. This feels like we're flying through the air across a river between the mountains, but none of this is real. All of this was generated on a computer. Now, there's lots of ways to explore fractals yourself. You may want to look for some freeware or shareware that allows you to either adapt someone else's fractal, make it your own by changing the colors and the shape and the shininess, or creating your own fractals. For example, this fractal to the left, the red, yellow, and blue one, I made using freeware. If you want to just see more fractals, you can visit my website with links to several of my favorite artists. These are beautiful, and I think my favorite one is Gumby Cat. She often hides cats in her fractals. Now, these are first generated by a computer to do the math, and then they use artistic software to work with the colors